To address the global microplastic pollution crisis, manufacturers have increasingly transitioned toward biodegradable plastics. The premise is straightforward: replace durable synthetics with materials designed to break down and reintegrate into the environment. We calculate the environmental impact of these materials using life cycle assessments, or LCAs. These assessments rely on a specific structural assumption. They model a managed, closed-loop system. This diagram outlines the standard boundary. Plastics are produced, used, and disposed of in engineered end-of-life facilities, like industrial composting plants. But in reality, biodegradable microplastics leak out of this managed loop. They bypass facilities and enter natural freshwater ecosystems directly. Treating the natural world as if it provides the same conditions as a controlled industrial plant obscures the data. It prevents us from measuring the actual consequences of these materials once they are subject to the chemistry of rivers and lakes. Unmanaged plastic in aquatic environments presents two distinct threats: the physical accumulation of particles, or aquatic ecotoxicity, and the release of greenhouse gases during decay. The current engineering priority is to maximize the rate of degradation in the wild. If a particle dissolves quickly, it limits the duration of its physical impact on the ecosystem. However, recent data reveals a trade-off. Engineering a plastic to break down faster in these environments is directly linked to a sharp increase in its greenhouse gas emissions. Traditional impact assessments fail to track this relationship. By treating toxicity and emissions as isolated metrics, the connection between physical safety and atmospheric damage remains unquantified. Without a new analytical framework, solving the physical microplastic problem may result in an unmeasured and significant increase in the climate impact of these materials. This diagram illustrates a fate model. It allows us to map exactly where and how a particle decays in an ecosystem. The top half represents the oxygen-rich water column. The bottom half represents the oxygen-depleted sediment bed. When a microplastic particle enters the water column, its trajectory is dictated by three variables: its density, its particle size, and its specific surface degradation rate. If it remains suspended in the aerobic water column, oxygen-dependent microbes consume it. This biological process degrades the plastic primarily into carbon dioxide. Two physical forces counteract this suspension. The inherent density and the physical size of the particle act as weights, pulling it downward toward the sediment. If those physical traits cause the particle to sink rapidly into the deep sediment, the environment shifts. Anaerobic microbes, which thrive without oxygen, take over. They digest the carbon structure and release methane. Methane possesses a significantly higher global warming potential than carbon dioxide, trapping more heat in the atmosphere over a 100-year period. The variable that determines which gas is released is the SSDR. This dictates exactly how much of the particle dissolves before it reaches the bottom. A plastic's environmental footprint is determined by a mechanical race, its rate of degradation against its rate of sedimentation. Whichever force wins decides whether the material emits carbon dioxide or methane. This scatterplot compares real-world data for microscopic 10 micrometer particles. We are mapping aquatic ecotoxicity on the horizontal axis against global warming potential on the vertical axis. Consider PLA. Its low degradation rate keeps it intact in the water column for longer. This results in high physical ecotoxicity, but it registers a low initial global warming potential because it is not yet generating methane. Now compare that to PHB. Its high degradation rate reduces the ecotoxicity threat. However, because it sinks into the sediment and undergoes rapid anaerobic decay, its methane production yields nearly 8 times the warming effect of PLA. This is known as a burden shift. By reducing the physical pollution, we increase the atmospheric hazard. This 100-year timeline tracks cumulative methane emissions to expose an accounting flaw in how we measure slow-degrading materials like PLA. Standard assessments use static GWP accounting. This model calculates total emissions as a single average stretched over the entire 100-year window. But the biological reality is time-dependent. A slow-degrading particle may sit inert in the sediment for decades, only releasing a concentrated methane payload 80 years later. A concentrated pulse of late-stage methane causes sharper atmospheric warming than a slow, continuous trickle of the same total volume. Applying dynamic GWP accounting, which weighs the timing of the release, shows that these delayed methane pulses are significantly more impactful than static models report. Relying on 100-year averages dilutes the measured danger of slow-degrading bioplastics, creating a false sense of climate security. This leads to a critical question for material science. At what speed must a bioplastic degrade to minimize its total climate damage? This graph plots a particle's degradation rate on the horizontal axis against its climate impact on the vertical axis. We often assume that faster degradation leads to a linear increase in emissions. The data shows the relationship is a non-monotonic curve. Along slope I, accelerating the degradation rate successfully feeds more carbon mass to anaerobic sediment microbes, which drives the warming potential up. This trend continues until the material reaches the SSDR peak. At this exact degradation speed, the material achieves its maximum fraction of methane production. The plastic lasts just long enough to deliver its entire carbon load to the sediment. The impact only begins to drop once the degradation rate is pushed past that peak into slope 2. Here, the plastic breaks down so rapidly in the aerobic water column that it vanishes into carbon dioxide before it can sink into the anaerobic sediment. Crucially, the location of this methane peak is not universal. It shifts based on the physical size of the manufactured particle. Demanding higher biodegradability without mapping a material's specific size against this curve risks unintentionally maximizing methane emissions. This bar chart breaks down the total cradle-to-grave emissions for 5 plastic types, comparing their decay in engineered facilities against decay in natural environments. Bio-based plastics are marketed as climate-friendly because plants used to make them absorb carbon as they grow, creating an initial offset. However, data shows decay in a natural freshwater environment can account for up to 94% of a material's total life cycle emissions. Because nature often converts that biogenic carbon into methane in the sanent, the initial carbon offset provided by the plants is mathematically neutralized. This contrasts sharply with engineered facilities like anaerobic digesters. In these controlled settings, the methane is captured and used for energy, which prevents the atmospheric damage seen in natural decay. Bioplastics only maintain their carbon-neutral potential if they are captured by industrial infrastructure. When they escape into nature, the carbon balance is lost. Current regulatory strategies often focus only on whether a material is highly biodegradable. This overlooks the specific environmental conditions where these materials actually end up. Materials engineers now have a clearer mandate. They must predict the environmental fate of microplastics based on their size and density before mass production. Engineers must use fate modeling to map degradation rates and consciously avoid the methane peak. We cannot allow the effort to solve physical plastic pollution to increase the atmospheric warming crisis. We must stop designing plastics merely to disappear and start engineering exactly